Hi. Today, my colleagues and I will present to you our project for programming for IoT application course at Politecnico di Torino called Mizu.Pot, a new era of plant care. Imagine when you buy a new plant, all you have to do is just take a picture of it and send it to a Telegram bot. And there, with the help of AI, it will tell you what is the optimal situation for this plant regarding light, temperature, and soil moisture. Furthermore, it can also measure these indicators and send real-time notification about them to you, and also manage the water level with its automatic watering pump. That's our vision. We use two different communication protocols in this product. REST service, which is commonly used in the majority of APIs nowadays because it's very scalable and flexible for retrieving, updating, and managing data. And also MQTT, which is very lightweight and very limited bandwidth usage and efficient data transfer, which makes it an ideal candidate for IoT device communication. Here you can see our system diagram. We have microservices, third-party services, and catalogs, and so much more. We will go into more details for each section later. When we were developing this platform, we didn't have in mind just one user. We thought about multiple users using this platform at the same time. That's why we use microservice architecture and Docker containers, and also multi-threading and asynchronous API calls and containerized microservices so that we can serve not just one, but more than one users at the same time flawlessly and smoothly. Catalogs. As you can see, we have resource and service catalog. In the service catalog, it's a first service that loads in our system and works as a registry because it holds the MQTT broker details and also the endpoints of our REST communication protocol. We use this in order to avoid hard coding this so the system can be more dynamic and efficient. In the resource catalog microservice, we essentially track of every data related to users, ways, and devices, and we keep them in the same place so we have a single source of truth throughout the whole platform. On the left side of the screen, you can see the service catalog, which has the chart service, data analysis, Gemini, and other endpoints details. And also on the right side of the screen, you can see the details about the different devices, users, and the last value of them. External integrations. We use PlantNet, Gemini, and Firebase as our third-party services. And for all of them, we use Docker. We use Docker to ensure isolation, portability, and scalability, and high availability, because there would be, instead of one system that if a fault occurs, everything goes down, they could continue working independently. We use Docker Compose and Portnair for web-based UI for easy monitoring and managing of these Docker instances. Here you can see a sample of our Docker files for our microservices. We use PlantNet API to identify the plant that the user has bought. So that we just send an image to this API, it returns with the name of the plant, and then we feed it to the Gemini API to get the optimal parameter ranges, user-friendly name, a short AI-generated care tip, and so much more. We also use Grafana Loki for our logging system to ensure a high reliability and efficiency. Hardware and device connector. We use ESP32 and different sensors in the systems. We use ESP32 because it's very low power operational microcontroller and very efficient. We use different sensors such as light sensor, photodiode, soil moisture sensor, temperature sensor, and ultrasonic sensor that serves in a way to detect if the water levels are lower than a certain level, so we can notify the user in order to prevent the dry reservoirs, and also the water pump. Here you can see a schematic of the sensors and ESP32 that just I explained. We use MicroPython because MicroPython can easily cover all the needs that we have, and in contrast to the Python, it's very lightweight and it's very optimized for use to be used in embedded systems. And the device connector, which is an embedded software which is running on our ESP32, is used to set up the initial phase and configurations and the communications. This is where the user connects via the Telegram bot and so much more. So it serves at device registration and user assignment, microcontroller and sensor configuration, and also the MQTT communications.
In this section, we are going to talk about microservices. As you can see, microservices divided into different parts, such as recommendation service, chart service, waste control, and etc. Bot notifier. The bot notifier acts as bridge between MQTT and Telegram, ensuring users receive real-time alerts about their plans. Its key functions are MQTT subscription and Telegram notifications. Chart service. The chart service provides a REST API to generate visual insights from sensor data, enabling users to track plant conditions over time. Key functions: data retrieval, JSON processing, chart generation, and export capability. This service enhances data-driven plant care, allowing users to visualize trends and optimize growing conditions. Data analysis. The data analysis service processes historical sensor data to generate useful insight for plant care. It provides a REST API for efficient data retrieval and analysis. Its key functions are data retrieval, JSON processes, smart data analysis, and user-friendly insights. Image recognition service. The image recognition service enables automated plant identification by interacting with PlantNet API through a REST API. Its key functions are image processing and forwarding, response handling and accuracy optimization, and a standardized output. Recommendation service. The recommendation service enhances personalized plant care by leveraging image recognition and AI-generated insights through a REST API. Its key functions are image processing, which is retrieves plant images and forwards them to the image recognition service for classification. AI-powered insight that calls the Gemini LLM API with a custom prompt to generate tailored care recommendations. Response standardization refines the AI response, ensuring consistency and relevance for the users. This service provides intelligence to accessible and optimized situation. Waste control service. The waste control service acts as decision-making engine for real-time device control, ensuring optimal plant care based on sensor data. Its key functions are MQTT subscription, threshold and device state management, and smart actuation logic. Firebase adapter. The Firebase adapter service acts as bridge between the MQTT network and Firebase, ensuring real-time data storage and analysis. Its key functions are MQTT data interception, data filtering and processing, Firebase integration, and this device ensures persistent cloud storage for of plants data.
All right, in this section, we are going to take a general look on our platform to see how it feels and how it looks like.
The whole platform is hosted publicly with public IP and host name on our server, exploiting Cloudflare tunnel, which ensure HTTPS security and cryptography. The whole system can be made with a single command line, exploiting Makefile script, which exposes a build command, a start, stop command, and a clean one. This translates to a Docker compose command of multiple microservices. You can also build just the logs part or the microservices part. This was especially useful in the first stage of development in order to debug the single microservice. We have also deployed a container instance in order to have an easy look of our platform status and the system log and check if all the containers are up and running and detect anomalies. We have also deployed a Grafana instance to retrieve and visualize all the microservice logs generated by Loki and Prometheus. Let's start the device, which automatically detects the start from a cold boot or hard reset, and we try to connect to any Wi-Fi. If no Wi-Fi is available, we start the access point mode with the smart face seed and a static IP. When the user presses the start button on the Telegram bot, it will automatically be registered to our DB or logged in if the user already exists. If the user is not based, you can add a new smart face to the button and following the steps, which basically are connecting to the ESP access point and click a button that will send an HTTP request containing the user ID, and we start a web interface to let the user configure the Wi-Fi on the device itself. The device recognizes the user through the user ID sent in the HTTP request and save it in a local storage file. Once is connected to the Wi-Fi, the device will push itself through a post API to the resource catalog, and this allows the auto configuration of new device without the manual intervention. As you can see from the logs, a new device is added successfully through a post request to the resource catalog. Once the device is linked to the user, the user can see the device inside the Telegram chat that is not yet configured, so you can go on set up the device through the Telegram bot. You will be asked to send a picture of the plant that will be redirected to the recommendation service, which ask and leverage the image recognition service in order to obtain the plant name from the PlantNet dataset. This name will be then sent with a custom prompt to Gemini to retrieve the best environmental condition and some suggestion that will be sent to the user about his plants. The device uses intermittent computing paradigm, basically going to sleep for a fixed period of time and then wake and send receive data. This is allowed by the MQTT event-driven async nature. Once wake up, the device will set the clock frequency to the lowest possible in order to save energy and trying to connect to a Wi-Fi saved configuration. It will then load all the GPIO pin and configuration of the sensor saved in a local file and collect all the values from the sensor and the measures and publish it on MQTT. It will then check for any actuation command sent through the MQTT and act if needed. The published data will then be intercepted by the base control and the TSpeak adapter. The base control check if the specific device ID surpasses certain thresholds and then decide if needed to send the actuation command, and TSpeak adapter forward the packets of data coming from the device to the TeamSpeak DB in order to be later then retrieved and analyzed. The TeamSpeak adapter exploits the fact that on first registration, the device pushing itself through a post API to the resource catalog. The resource catalog will also create dynamically a new channel on the TeamSpeak platform and assign it to the device. So the TeamSpeak adapter can read the channel key and push directly on the new channel. This is done dynamically in order to ensure the scalability of the project.
Now we can see how our Telegram bot can also provide real-time sensor data and some advices for the user. The data analysis service is responsible for this. Here, the container view of the logs of our data analysis container. And here, we start our bot after the login as we saw before. We can select our plant. And we can see how we have all the real-time data value and a suggestion by our data analysis service. Here, we can see how the temperature alert is set to low, so to the user, the message appears that the temperature is too low. This service analyzes the historical data and searches for any condition of the plant that are not recommended, in this case the temperature. It compares the value with the threshold that are retrieved by Gemini or set by the user. The user can inspect the temperature in this case, or any other sensor's value by clicking it. So we can see the temperature now. The user can plot the charts of the collected data by the sensors. He can decide and select the charts